Let me know if this situation sounds familiar to you. You're in some class and you've been given an assignment. Maybe it's a research paper, maybe it's a presentation. So you write a draft and you send it to your partners. And then you revise the draft, send it to your partner again, finish it up, send it to your partner again, make some last-minute changes, send it to partner again. Promise this is going to be the last version, send it to your partners again. Oh, wait. While you were writing the seriously, I promise it's final version, your partner fixed a couple of typos. So now you have two versions, you have to merge them, you miss some of their typos, you lose a few marks, everyone is sad. But fortunately, we have solutions to these sort of problems now. Among the coolest cloud apps to have come out in the recent years are apps like Google Docs and Dropbox Paper, where multiple people can edit the same document at the same time. If you've ever used one, you probably know how incredibly convenient they are. You can brainstorm at the same time, you can work on different or the same bits of the project at the same time, you can fix other people's typos. And to support that, these applications need a way to resolve conflicts that happen when two users change the same text to different things at the same time. These applications also enable having a single source of truth, which means that there's only ever one version of the document alive at any given time, so you don't have to chase down all your teammates' version of the document. And that also requires a way to resolve editing conflicts. So the goal of this talk is to give you an idea of how these algorithms for conflict resolution might look like. And first, let's just start by looking at an example to see what might make this a hard problem to solve. Let's say you and I are working on the title of this talk. It's definitely going to include build a text editor, and we might have our cursors at different places because we want to change different things. I want to add build a cool text editor, and you want to write how to build a text editor. If we have a very naive way of synchronizing these changes, we might just do something like this. I'll send you the change insert cool at column 8, and you can send me insert how to at column 0. But originally, when I wrote cool, column 8 pointed after the letter A. But when you receive the message, column 8 points after the letter B because you've inserted something before it. So when you apply the change, you'll get some gibberish like how to cool build a text editor. And everyone is sad again. So to resolve these kind of editing conflicts, I'm going to present a class of algorithms called conflict-free replicated data types, or CRDTs for short. It is not what Google Docs and Dropbox Paper use. They use something called operational transform. But I believe that CRDTs are quite a bit easier to understand, especially in 10 minutes, and they will generalize better to things other than text documents. So the first step we'll need to build a CRDT is to understand the importance of commutative operations. So earlier, we got an editing conflict because our operations did not commute. Inserting at column 0, then column 8, is not the same thing as inserting as column 8, then column 0. But let's imagine, and let's not worry about how for now. Let's just imagine that every single operation that the user did was commutative. So the user makes a bunch of changes, and I can rearrange them in any order, and I'll still get the same result in the end. Now, if this is true for all users, can you see how this might make synchronization really easy? Because two users can be doing completely different things separately, send each other their operations at a later time, and because the order in which operations get applied doesn't matter, each user can be applying their operations and the other person's operations in a different order, and you'll get the same result on every client, and you'll get something very consistent. A very trivial example of a CRDT that has this property would be an add-only set. It doesn't matter in which order you add things to a set. It's always the same set in the end. Now, technically, you don't need operations to be commutative. You only need them to be sort of interleavable. But I like to use the word commutative because it's easier to think about. And the second property we'll need is for operations to be idempotent. Sounds like a big word, but it only means that if I apply the same operation twice, it's the same as applying it only once. This is useful, for example, if two users delete the same character at the same time. This should only cause one character to be deleted. So that's cool, but how are we going to design these commutative operations? So first, let's look at how we could implement a synchronized bag data structure. A bag is like a set, but you can have multiple copies of the same item. Like a bag of kiwis, for example. All these kiwis are the same, but you can have multiple kiwis. And this bag should have two operations: add a kiwi and remove a kiwi. So let's say we start with a bag that has one kiwi in it, and there's 3 people editing this bag, each with their local copies. 2 of them decide to remove a kiwi, and 1 of them decides to add a new kiwi. First, we apply the operations locally, and then send each other the messages of what we just did. Now, what do you think the end result should be? Like, probably only 1 kiwi in the bag, right? Like, we had 1 kiwi, we removed it, but we added a new different kiwi, so we have the new kiwi in the bag in the end. But in this situation, what will happen is that the bottom kiwi, the bottom bag, will have no kiwis in it because it received 2 remove kiwi operations. And the top 2 bags will either have 0 or 1 kiwi, depending on whether the add message or the remove message arrive first. So we got an inconsistent state on different clients. They see different things. That's not very good. But we could change a little bit how our operations are designed. We could change the add operation to not only add a kiwi to the bag, but give the newly added kiwi a unique ID. And we're going to generate this ID in such a way that no client has ever used this ID before, ever. And the remove operation can take not just a kiwi to remove, but a particular kiwi to remove with a particular ID. Now, if I do the same thing as before, remove in 2 bags and then add in 1 bag, I'll find that after sending out the messages, I'll have the second kiwi in every bag. The bottom bag received 2 remove kiwi messages, but both requested to remove kiwi number 1, and kiwi number 2 was never touched. And different add and remove operations are never going to conflict because they're operating on completely different elements. So that's a neat trick, but you didn't really come here to hear me talk about grocery shopping, right? You want to know about text editing. But OK, I mean, a grocery bag isn't too different than a text document. I mean, if you just replace the kiwis in the bag with alphabet cereals, you got more or less the same thing. The only difference is, usually when you have a text document, it's implied that the characters come in some order. So what we're going to do is we're still going to use a bag data structure to store the characters in our text. And of course, you can have multiple of the same character in a text. And each of them are going to have their own unique IDs. But the order of the characters in the text is going to be implicitly determined by the order of the IDs. That is to say, the order of the characters in the text is the same as the order in which the IDs come. You just sort the characters by their ID, and you get the text. So again, that's neat, but like in this case, how do you insert between 2 characters? Like, I don't know if any of you noticed, but I misspelled the word occurrence. It's supposed to take 2 R's. So how do I add the missing R? The 1 R is ID 5, and the E is ID 6, so how do I insert in between? Well, the trick is pretty simple. You create a fraction. If you don't have room between 5 and 6, you just make an ID with 5.5. So that's pretty simple. But we do want to generate unique IDs. And in this case, that doesn't work because if 2 different people decide to fix this typo and insert a character R at the same time, they'll both generate IDs 5.5. And we want the IDs to be different. So the last step is going to be to combine fractional indexing with unique ID generation. Let's say we have two users editing the same text, a duck and a turkey, because it's boring if it's always humans, plus there was no goose emoji yet, so a duck it is. The duck types water, and that's straightforward. You generate IDs 1 to 6. But we're also going to tag these IDs with the site ID of the duck. And then when the turkey wants to add something like Lou, there's, again, no room between ID 5 and 6. But that's all right. You can just create IDs 5.1, 5.2, 5.3, 5.4. But the new digit of these IDs, which represent fractions, is going to be tagged with the site ID of the turkey, because the turkey inserted those characters. And if the duck decides to troll and add a honk, it's going to run out of space again. So we're going to create a new ID with a third digit, and that's going to be tagged with the ID of the duck again. The last edge case we want to solve to generate unique IDs on character creation is if the same user deletes and reinserts the same character. Even with the site IDs, that could still generate the same fraction. So we're just going to add a timestamp or an incrementing counter on every client, and that solves that problem. So now, whenever we typed a new character, we're always going to generate a unique ID, which is going to consist of a timestamp plus a list of pairs of digits and site IDs. Deleting characters still works as in the bag of kiwis. Instead of giving it a character to delete or the position of a character to delete, you're going to give it the ID of a character to delete. So now, every operation always operates on unique elements. Therefore, operations are commutative. And as we discussed at the very beginning, since operations are commutative, then synchronization becomes trivial. And that's pretty much it. I mean, there's a bunch of implementation details which I haven't gone into, and I'll link to my blog post, which goes into more of these details. But what I hope this talk was helpful in doing is to give you an intuition on how you might design operations so that you can have a collaborative editor, text or otherwise. And we do it by designing operations in such a way that they never conflict at all. Makes for us fun side projects, could be useful at work. And I hope you found this talk useful. I put my contact information on the slides. My name is Rudy. Feel free to check out my blog for a more detailed write-up of this technique. And thank you for your time.